Basically what Newton's law of gravitation says is that every object that has mass is attracted to every other object that has mass with a gravitational force. I'm going to sketch two objects and then talk about that force. Here are two objects, M1 that has some mass in kilograms and M2 which has some different mass but also in kilograms. These two objects are not necessarily the same size, but their centers of gravity are indicated with these dots that are kind of at the geometric centers of the spheres. We're going to say that these two objects are separated from each other by some distance that I'm going to call r, and I'll usually measure this distance in meters. What Newton's law of universal gravitation says is that these two objects mutually attract each other. And the force of attraction is given by some formula. The formula says that the magnitude of the attraction is equal to some constant, which we're going to call capital G, that's called the universal gravitational constant, more about that in a minute, times the product of the masses, M1 times M2, divided by the square of the distance between the centers of gravity of object 1 and object 2. We're not going to bother with where Newton came up with this. He had some reasoning that he used, but nevertheless, this is the formula that we're going to use, and we're just going to take it as a given. It turns out to be very successful. People got to the moon as a result of using this formula, and so we're going to take it as a law that we can use to make calculations. Now notice this is a vector force. The direction of the force is going to be in a direction that's on the line that connects the centers of gravity with each other. And each of the objects feels this force. The strength of the force that's exerted on object 1 by object 2 is equal in magnitude to the force that's exerted by object 2 on object 1. Here's how we'll indicate that with a vector. We're going to say that the force that object 1 feels due to object 2 is given by an arrow that looks like that. And this F with a subscript 1, 2 means the force on object 1 due to object 2. Likewise, there's a force that's experienced by object 2 due to object 1. It's going to be along that same line. The magnitude of that force is going to be equal to the magnitude of the force on object 1 due to object 2, but its direction is going to be opposite. These two forces are numerically equal to each other, but their directions are opposite. So we'll write that in this way. Now, we're going to see that here is a hint at Newton's third law. Basically what it says is the force that object 1 experiences due to object 2 is going to be equal in magnitude and opposite in direction to the force that object 2 feels as a result of object 1. Those two forces are equal in magnitude, they're opposite in directions. We're going to call these action and reaction pairs. We'll have a lot more to say about action and reaction pairs in the coming days. Now what about this constant capital G? That's going to be a fundamental constant. It's going to be a number that's going to be the same number in every problem that we use that involves Newton's law of universal gravitation. Here's what it is. G is equal to 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. And in a moment I'll point out to you the fact that this is found on a fundamental constant sheet that you're going to receive on the AP exam. It's a number that will appear on the multiple choice section as well as on the free response section. But it's a good friend to have, and it's one that you'll probably end up memorizing as a result of doing all these problems. You'll use it enough that it'll be a number that just comes to your mind, just like the acceleration due to gravity is 10 meters per second squared. In fact, there's a relationship between capital G and little g, the acceleration due to gravity. Let's see what that relationship is. So I'm going to scroll down a little bit. Let's remember that this G stands for 10 roughly meters per second squared. And we say that I have a weight that I can calculate if I know what my mass is. And my mass is some number that I would feed in to the weight formula. We say that this weight is a force that the Earth exerts on me as a result of my mass and its mass. Well now, if the Earth is an object that has mass, and I am an object that has mass, and I'm standing on the Earth's surface, then there must be some attraction between my center of gravity and the Earth's center of gravity. That's a gravitational attraction, and we're saying the weight is that gravitational attraction. So let's call me object 1. This is the mass of Haynes here. And let's call the Earth object 2, and we'll say that the mass of the Earth is concentrated there at the center of the Earth. Now, there's some distance between me and the Earth. All right, now the Earth is huge. Its radius is several thousand kilometers. In fact, its radius is going to be some number that we're going to need in a moment. In fact, if you look on Roman numeral page 17 of your textbook, you're going to see that there's a table there that says Planetary Data, and the radius of the Earth there is given as 6.37 times 10 to the 6 meters. That's roughly 6,370 kilometers. My center of gravity is located about a meter off the ground, and what I claim is that that meter off the ground that separates my center of gravity from the ground is essentially negligible compared to this 6 million meters between the center of the Earth and the surface of the ground. So that I'm going to say that the distance between me and my center of gravity and the Earth's center of gravity is essentially equal to the radius of the Earth. On that same page, Roman numeral 17, you're going to see that there is a number for the mass of the Earth. And that number turns out to be 5.98 times 10 to the 24 kilograms. My mass is roughly 75 kilograms, but we're going to see in a moment that that number is actually going to fall out when I do some math here. Now, what are we trying to do? What we're trying to do is we're trying to see what is the relationship between this little g, the acceleration due to gravity, and universal gravitational force that Newton gave us. What I claim is this weight is that gravitational force. In other words, my weight on the surface of the Earth is equal to the gravitational force of attraction between my mass and the Earth's mass. Well, let's feed some stuff in. My weight is equal to m times g. The gravitational attraction between my center of gravity and the Earth's center of gravity is given by Newton's universal gravitational law. G times m Haynes times m Earth divided by the distance between our centers of gravity, which I claim is roughly the radius of the Earth. That number squared. Now there's something that appears common on both sides. It's the mass of Haynes. Well, using the rules of algebra, I can just cancel that out. The mass of Haynes disappears on both sides, which says that this number g, the acceleration due to gravity, is equal to big G times the mass of the Earth divided by the square of the radius of the Earth. In other words, the local acceleration due to gravity at the surface of this celestial object is equal to this capital G times the mass of the object divided by the radius of the object squared. Let's put in the numbers that we know, and let's see what number that comes out to be. So big G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram. Multiply that by the mass of the Earth, 5.98 times 10 to the 24 kilogram. Divide that by the square of the radius of the Earth, 6.37 times 10 to the 6 meters. And I've got to square that number. I'm going to feed all that into my calculator and see what comes out. When the smoke clears, my calculator says I get 9.83 roughly meters per second squared. 9.8 meters per second squared. That's almost equal to 10. That's the number we've been using. And in fact, that 10 meters per second squared is going to be the number that I encourage you to use on all your weight problems. Now you see where that number comes from. It comes from physical data with respect to the Earth and Newton's law of universal gravitation. You want to figure out what's the acceleration due to gravity on the surface of the moon? You play the same game. Put in G, put the mass of the moon in, put the square of the radius of the moon in, put the numbers together, you're going to get some number. What's the acceleration due to gravity at the surface of Jupiter? You put in the information for Jupiter. Basically, you can figure out what the acceleration due to gravity is at the surface of any planet or due to any object if you're some distance away by using Newton's law of universal gravitation. I don't know about you, but I think that's pretty cool. I don't think that you need to memorize it, But this formula relating the acceleration due to gravity, little g, and everything else, the g me over re squared, is kind of a useful thing sometimes to remember, but it's easy to derive if you can remember that the weight is basically the gravitational force. If you scroll down, you're going to see that there's a constants page that I have inserted here, which looks something like page Roman numeral 16 in your textbook. And what you're seeing here is the table of information that was given on the 2004 and the 2005 AP Physics B exam. And what I want to point out here is that one of the fundamental constants that's given is the universal gravitational constant. It's right here. And you'll see that right underneath it is the acceleration due to gravity at the Earth's surface, 9.8 meters per second squared. But again, you use 10 and they'll give you full credit for it. While we're here, let me just check off a few things that I think you're going to find most important as you get ready for your AP exam. Proton mass, electron mass, neutron mass, charge on the electron, Avogadro's number, that's going to be important. Universal gas constant. I don't think you're going to see Boltzmann constant. Speed of light, Planck's constant. That's going to be a quantum mechanical thing, and you're going to see it both in units of EVs times seconds and in units of joules times seconds. And the combination of Planck's constants times the speed of light is a useful one, though that's something that's easy to derive. Coulomb's law constant, this K, in terms of 1 over 4 pi epsilon naught. I don't think you're going to see the vacuum permittivity that much, but you're going to see the combination 1 over 4 pi epsilon naught. It doesn't mean much to you right now, but you'll see when we get into electricity that it will. Moving on down the page, I think you'll see that the electron volt and the atmosphere are also going to be constants that you'll use. Don't worry about those right now, but I wanted to point them out to you so that as you're using problems, as you're solving problems, these constants are things that you're going to end up using. And some of them will turn out to be good friends that you'll remember because you use them so much. All right, so now let's work some numerical problems. And the one that I would like to take a look at is example 16.1 in your textbook. On page 118, we read this. Use Newton's law of gravitation to calculate the force of gravity of the Earth on a 1 kilogram mass on the surface of the Earth. And we call the weight the gravitational force, but they're actually wanting you to use Newton's gravitational law. We know that the weight is going to be about 10 newtons, because we know Fw is equal to m times g. 1 kilogram times 10 meters per second squared is going to be 10 newtons. But let's do it their way. Here's the Earth with its radius and mass. There's the 1 kilogram object that's on the surface of the Earth, and its center of gravity is essentially located a distance of the radius of the Earth away from the center of gravity of the Earth. So let's use our formula. Notice that I'm putting the radius of the Earth in because that's the distance between the centers of gravity of the two objects. There are the numbers, and now I want to calculate what that gravitational force is. So I feed the numbers into my calculator, and I get some result. Lo and behold, 9.83 newtons, which is roughly equal to 10 newtons. Let's go to part B. We want to do the same thing for a 100 kilogram mass. We have a similar picture. So I'll approach it in a similar way. Use the formula, but I'm going to put 100 kilograms in for the 100 kilogram mass. So there it is with the numbers inserted, and now I'm going to put that into my calculator and get some result. I get 983 newtons, which is roughly 1,000 newtons, which I would have gotten with the regular weight formula. And just for kicks, I've written the weight formula down with its result, and we'll see that these two results, the 983 newtons and the 1,000 newtons, mean the same thing. All right, part C talks about the gravitational attraction between a 1 kilogram mass that's in orbit 250 kilometers above the surface of the Earth. This one is a little bit more tricky, and I don't like your textbook's diagram of this, so I'm going to draw it a little bit more carefully. Here's a diagram of the Earth that I've sketched a little bit bigger, and let's make an assumption here, which is not unreasonable, which is that this orbit is circular. The orbit is 250 kilometers above the surface of the Earth. Now the radius of the Earth is 6,370 kilometers, roughly 6,400 kilometers. How high in this diagram above the surface of the Earth is the satellite? What I claim is that if you take the distance that the object is above the Earth's surface, 250 kilometers above the Earth's surface, and divide that by the radius of the Earth, what you're going to get is 0.04. In other words, the distance the object is above the surface of the Earth is roughly about 4% of the radius of the Earth. In other words, this object is about 4% above the Earth's surface. If it were in orbit around the Earth, in a circular orbit, it's not going to be very high above the Earth's surface. I'm going to call this distance between the surface of the Earth and the satellite that's in question, the 1 kilogram satellite, I'm going to call it h. And I'm going to call the distance between the centers of gravity of the Earth and the satellite the radius of the Earth plus this distance h. And that's the number that I've got to feed into Newton's law of gravitation. Now, hang with me on this. There's a point that I want to make, and it's a point that we'll come back to when we deal with orbits. The distance I'm going to feed in for the distance between the center of gravity and the Earth is going to be the sum of those two distances, which is roughly 6370 kilometers plus 250 kilometers. And when I add those two numbers together, I get a result, which is 6620 kilometers. But I need that in terms of meters. And a kilometer is equal to 1,000 meters. So I'm going to end up with the number that I put into Newton's law of gravitation as 6.62 times 10 to the 6 meters. So let's feed that into our formula. There's the formula, but now the distance I'm going to put in is the distance between the centers of gravity of the satellite and the Earth, which is not the radius of the Earth, it's the radius of the Earth plus that little height that the satellite is above the Earth. All right? So there are the numbers, and when I put that into my calculator, I get some result. I get 9.1 newtons. What? This object that's in orbit above the surface of the Earth has a gravitational force of 9.1 newtons, while on the surface of the Earth it has a gravitational force of 9.8 newtons? Mr. Haynes, I thought that things in orbit are weightless. Ha! That's a tricky term, weightless. They aren't weightless. They still have weight. This gravitational attraction between the object in orbit, this 1 kilogram mass that's in orbit, 250 kilometers above the surface of the Earth, in the space shuttle, roughly, if you want to think of it in that way, still experiences a gravitational force that's nearly as big as it is on the surface of the Earth. Something else must be going on that causes it to appear weightless. And that something else is going to be the subject of another lesson. I'll give you a hint, though. The object is not experiencing zero acceleration. It's experiencing free fall acceleration at the height that it is, and everything else around it is also experiencing acceleration at the same rate. It is falling around the Earth, and that's what gives it this appearance of weightlessness. More about that another time. So, what we've seen is that there's a universal gravitational force. We've seen what the formula is. We've computed some numerical examples, and now we're ready to go on to other things.